Alright, section 9.3 talks about matched pairs. We define two sets of observations are paired if each observation in one set has a special correspondence or connection with exactly one observation in the other set. An example, we have three of them. State if the samples are dependent or independent, and whether the variable is qualitative or quantitative. So are you measuring quality or quantity? And do you think those two samples are dependent or independent? Among competing acne medications, does one perform better than the other? To answer this question, researchers applied medication A to one part of the subject's face and medication B to a different part of the subject's face to determine the proportion of subjects whose acne cleared up for each medication. The part of the face that received medication A was randomly determined. So subject 1, we could say medication A on part of the subject's face. Sample 2 would be medication B on parts of the subject's face. The variable, what you're trying to figure out here is whether the acne cleared up or not. What proportion cleared up? This is, of course, dependent. It's on the same face, and it is a quality. Another example would be a researcher wishes to determine the effect of alcohol on people's reaction time. She divides 100 people 20 years or older into two groups. Group 1 is asked to drink 3 ounces of alcohol while Group 2 drinks a placebo. 30 minutes later, they measure their reaction time. So here, variable 1 would be the 21-year-old, 21-year or older, who drinks 3 ounces of alcohol. Group 2, 21 years or older, who drinks, how many? Is it? 3 ounces. Who drinks 2 drinks of placebo. And what you're measuring is a person's reaction time after 30 minutes. Those are independent. The samples are, and it is a quality as well. Example 3. A statistician wants to compare the treatment of females and male actors based on their gender. She looks at the age of a female or male who won the best actor or actresses in the last 5 years of the Oscar. So the first variable is here. You could say the male, you could say the female. Let's go with the female. The female actresses who won best, what was it again? Best actress in the last 5 years of the Oscars. Group 2 would be the males, will be the male actors who won best actors in the last 5 years of Oscar, and the variable here is treatment of actors based on gender. Based on, not gender, based on their age. Those are dependent and qualitative. Here we have two samples. Consider an experiment where a researcher throws a stick towards someone and first asks them to catch it with their dominant hand and then again with their non-dominant hand. The time below shows how long it took several individuals to react to the toss. So these are dependent samples because it's the same subject. They did the dominant hand, the non-dominant hand, and they figure out the difference between them. And they sum the difference. Now, since the sum is negative and you're subtracting those, if the sum is negative, that means the non-dominant hand is dominating over the dominant hand. Now, we create one new sample of difference, then run a test, which is matched pair. Which is the t-test. True mean of difference, the population difference between those. The standard deviation, it's again the sample, and n is the sample size. So we notice here that, well, the logic between the difference being 0, the null hypothesis is going to always say the null is 0, and the alternative will see it's either less than, greater than, or not equal. So if d equals 0, then we fail to reject the null hypothesis. And if it's bigger, we fail to reject the null hypothesis. If it's off by a little, we fail to reject the null hypothesis. And by a lot, we reject the null hypothesis. And you need to know, is the claim with the null hypothesis or not? And what does it mean by a lot? We did this too many times. The prerequisites, or where you check, the samples are dependent and simple. So they have to be dependent. N is greater than or equal to 30 or none. Hypothesis testing always says the difference is 0, means those didn't change. The alternative is less than, greater than, or equal. You know how that works. One of them is a left tail, the other is a right tail, and one of them is two tail. And alpha should be given. If not given, we use 5%. The test statistics is given by d. This is going to be always 0 because the null hypothesis assumes it's 0. Divided by S of d divided by the square root of n. That's my test statistics. We have a left-handed, a right-handed, and both a left-handed, right-handed, or left tail, I should say. That's what I meant to say. left-tailed, two-tailed, and right-tailed. And we could use the p-value or critical value and make a conclusion, and you know the drill, we're going to do both. So I'm looking at the first example, and here we are. It is commonly held belief that crossovers are safer than small cars. If a crossover and a small car are in a collision, does the crossover sustain less damage as suggested by the cost of repair? Consumer reports crashed crossovers into small cars, with the crossover moving 50 miles per hour and the front of the crossover crashing into the rear of the small car. The data is normally distributed. Very good. Below are the repair costs. So we're trying to see if the cost is going to be less. So Lexus RX 350 into Honda Insight. The small car damage, the Honda was $1,274. The crossover was $1,721. So if I take the difference of those, this would be a negative 447. Here, 2214. So this is positive 893. So I'm subtracting those in that order. This is 2373. This is 271. This is 1680, 1916, and 1676. Does the data suggest that the crossover are safer? Well, let's see. Use 1%. Null hypothesis is that the difference, the mean of the difference is 0. It didn't change. Alternative, the mean of the difference is bigger than 0. And the claim, we're checking to see if it's gonna be significant. The t-test, well, we have an issue. I don't have the average and the standard deviation. I could get my calculator. Oops, the wrong calculator. I can get my calculator and I could input those values. So we go for statistics, edit, and we have negative 447, 893, 2373, negative 271, 1680, 1916, and 1676. That's 7 of them. And if I go to statistics, calculate, here it is. So if I copy down what that says, I just need a few of those. I don't need a whole bunch. So what I need out of this, I need the average. And here, the average happened to be, and the standard deviation. Standard deviation would be 1100.62. Alright, that's pretty much all I need out of this. And now I would go ahead and say, well, the test statistics is d minus u sub d divided by s sub d divided by the square root of n. We got the average to be 1117.14 minus 0 divided by the standard deviation 1100.62 over the square root of n, and n happened to be 1, 2, 3, 4, 5, 6, 7. And if I throw this in the calculator, I would take 11 17.14 divided by 1100.62 divided by the square root of 7 as I see it. It equal, and I'm getting must have messed up somewhere. I lost something. 1117.14 divided by 1. That's odd. Let me check really quick. Oh, standard deviation can't be that big. Let me double check that. Okay, I'm gonna go back to the calculator. I recalculated a bit. So here, maybe I should do this. 1117.14 divided by parentheses 1100.62 divided by radical 7. There it is. That's more like it. So here we are. .685, I suppose 6.9 will do, it doesn't matter. So let's go with the p-value. The p-value, what's the probability that t is greater than 2.685? I'll get my calculator and I'll go for my distribution. This is normal TCDF, and I want a 2.685. The upper is 1 e to the 99 degrees of freedom. There were 7, so 1 minus 6. And I get that probability to be 1.8%. Remember, they changed, it's not 5% in this case. They made alpha here equal 1% only. So we would pretty much fail to reject the null hypothesis. Let's go for the test statistics. If I want a right side of being 0.01, well, we know how the t-distribution works. It only works to the left. So if I go for the cutoff, if I go for the inverse t-distribution, and I want an area of 0.99, degrees of freedom is 6, tell me what that number is, 3.14. And you notice 2.86 does not fall in that rejection region, so we failed to reject the null hypothesis. What's your conclusion? Remember, we failed to reject the null hypothesis, and the claim wasn't in the null hypothesis. So we say there is not sufficient sample evidence to support the claim. That crossovers sustain less damage than small cars. So that's really how it works. Another way of testing claims is to look at the confidence interval and see if 0 is in it, you fail to reject the null hypothesis. If 0 is not in it, you reject the null hypothesis. And we know D, which is the point estimate for the average, error is given by this formula that's provided. So it didn't change much between this and the previous section. It's still the same thing. And of course you take D plus or minus E, that gives you the interval. So here we have a company claims that its 12-week special exercise program significantly reduces weight. A random sample of 8, n equal 8, 1, 2, 3, 4, 5, 6, 7, 8, was selected, and some of the following tables, and the following table gives the weight in pounds of those 8 people before and after the program. So here's before, here's after. If I look for the difference, that would be a -5, that would be a -8, that would be a -6, a -2. These are the same. This is a -5, this is a +2, and this is a -3. Now, if I am to go ahead and let me clear that. Okay, good. So if I was to go ahead and input a -5, a -8, -6, and -2, 0, -5, a 2, and a -3. Where did that -6 come from? That's a 2. And that's a -3. That's odd. Okay, -5, 0, -2, -6, -8, and okay, very good. So if I quit and I go to stat, calculate, and give me those values, there it is. So what do I need out of that? I just need 2 values, really. I need the average and the standard deviation. Well, they tell me the average here is -3.375, and the standard deviation is 3.292 if you want. That doesn't mean it's the same thing. So how does that work? Determine T sub alpha over 2, and if I look at alpha, did they give us that? They didn't, so we're going to make it 5%. Always two-tailed for those. So this is 0.025. I could say T sub alpha over 2 is going to be, and I'm going to go for the inverse T distribution. The area, let's say the area to the left is 0.025. Degrees of freedom, we just measured it. What was n? N was 8, so this is 7. The probability, no, I'm sorry, not probability. The T sub alpha is -2.36. 2.36. Do I need to round more? No. So this is 2.36. Got it. Margin of error is really that is 2.36 something's not matching. Okay, I was looking at my notes. Something's not matching this. They do say what the confidence interval is. So this is really not 5%. This is 5% each. So I gotta change that value really quick. And if I am to go ahead and do it on the calculator, do it again. T distribution, we want the 0.05, everything else is the same, and we're getting okay. What the heck? So that is 1.895 and negative 1.895. So this is 1.895. Standard deviation happened to be 3.292 divided by the square root of 8, we said. That turns out to be, I need to guess, 1.895 times 3.292 divided by square root of 8. 2.21, 2.206, or 2.21. And the confidence interval is pretty much D plus or minus the error. So that would be, D we said was negative 3.375 plus or minus 2.206. That would give the following interval. And if I take negative 3.375 minus 2.206, negative 5.581, and if I go in there and I add, negative 1.169, and in this case we would say, since the interval does not contain 0, it appears that the weight loss program is